Assalamu alaikum, my dear respected student. Today, I'm going to discuss the reaction of alcohol. It is the second lecture on alcohol. Previously, we have discussed the synthetic scheme and some nomenclature of alcohol. In today's lecture, we will try to cover these topics like reactions of alcohol and conversion of alcohol into alkyl halides and tosylate, and converting alcohol into tosylate, mesylate, and triflate, and a good living group. Then Williamson Ether Synthesis, and the last we have the summary reactions of alcohol. When we look at the structure of the alcohol, the reaction of alcohol mainly to do with the following. The oxygen atom of the hydroxyl group of the alcohol is nucleophilic and weakly basic, and the hydrogen atom of the OH group is weakly acidic. The OH group can be converted into a good living group so as to follow the substitution or elimination reaction. This is the structure of the alcohol. You can see here, as I mentioned in the previous slide, that alcohol, this H is acidic, and from this oxygen is nucleophilic, and it is a polar structure as well. Protonation of alcohol convert into a good living, individually, of course, alcohol, the OH is a poor living group, while protonation makes alcohol into a good living group in the form of the water molecule. For example, when alcohol treated with the strong acid to give you the protonated alcohol, and which ultimately by any nucleophile can be eliminated or substituted to give you this substituted product as well. These are some reactions that alcohol could be converted into alkyl halide when alcohol treated with the HX, like X could be chlorine, bromine, or iodine, we have the alkyl halide. And similarly, when alcohol treated with the PBr3, phosphorus tribromide, we have the alkyl bromide. When alcohol treated with the thionyl chloride, we have the alkyl chloride as well. Let's see. When alcohol treated with concentrated acid at room temperature, we have the major product, which is the substituted product. And when we increase the temperature, like more than 100 or 90, this substitution is being converted into the elimination. We do not have the substituted product at high temperature. Another example, when alcohol treated with the PBr3, we have the bromine. Bromine is being substituted the alcohol to give you this alkyl bromide in 63%. Here is the order of reactivity of alcohol on treatment with the HX, like HCl, HBr, or HI. The most reactive alcohol is the tertiary alcohol, and the least reactive alcohol is the methyl. While order of reactivity of the hydrogen halide, the strongest acid is the HI and then HCl. And HF is generally unreactive in this reaction because of the strong attraction between the hydrogen and the fluorine. Let's see the mechanism of the reaction. It follows the first step is the protonation from the acid to give you the oxoniamine. And the second step, the slow step, the formation of the carbocation, especially when alcohol is a tertiary alcohol. In the next step, the attack of the nucleophile, like from the halide. In this example, we have the chloride ion, which acts as a nucleophile to give you this alkyl halide. Primary alcohol and methanol react to form alkyl halide under acidic condition by SN2 mechanism. The previous example was the SN1 mechanism. The primary alcohol, when the first step I'm just showing here the form, let's see that the acid has protonated already the alcohol. Consider this alcohol already reacted with the hydronium ion. Now in this specific example, the halide, which could be chloride or the bromide or the iodide, is being attacked at this carbon of the primary alcohol to give this substituted product. Let's discuss some more reactions of the alcohol with PBr3 or the SOCl2 thionyl chloride. The first reaction with the reaction of alcohol with the phosphorus tribromide. Alcohol, when reacted with phosphorus tribromide, If alcohol is primary or secondary, this reaction is very good. The tertiary alcohol is give you very poor yield or unreactive with this PBr3. Okay, this reaction does not involve the formation of the carbocation and usually occurs without rearrangement, of course. And we have already seen that the tertiary alcohol generally give you the carbocation formation. So this is basically the example of the SN2 reaction as well. Okay, here the first step, the mechanism that alcohol is reacting with the phosphorus tribromide. Alcohol oxygen is acting as a nucleophile and phosphorus acting as a Lewis acid to give you this intermediate, and the bromide ion will depart and we get the protonated alkyl dibromophosphide. Now the bromide ion which was depart from here, which now is being attacked at this carbon to give you the substituted alkyl bromide, and this intermediate will depart. Okay. This step will continue until and unless we will get the 3 moles of alkyl bromide, and ultimately it is being converted into H3PO3, H3PO3. Okay. Second, the next mechanism is the reaction of alcohol with thionyl chloride. Thionyl chloride also react with 1 degree and 2 degree alcohol to give you alkyl chlorides. And as with PBr3, the reaction does not involve the formation of a carbocation and usually occur without rearrangement of the carbon skeleton. Okay, and pyridine is often used in this reaction, which actually promote the reaction. There are two purposes of the pyridine, that one as a solvent and other to neutralize the acid formed during the reaction. Let's see the mechanism. The first step, the attack of oxygen of alcohol as a nucleophile on the empty orbital of the sulfur of the thionyl chloride to give this intermediate. And in this case, the oxyanion of this intermediate will collapse to depart this chloride ion to give you this intermediate. Here, the base will abstract, which is the pyridine and which is also a solvent, will extract the proton to give to ultimately this proton, which is captured by the chloride ion to give it this intermediate along with the removal of the HCl. Right? Now, what happened? This ROSOCl. Now, pyridine act as a nucleophile to depart the chloride ion ultimately to give you this intermediate. Now what happened? This chloride ion which is being departed from here will act as a nucleophile over this carbon and ultimately evolve a sulfur dioxide gas along with the pyridine, and of course the required alkyl halide as well, which is the alkyl chloride in this specific example. Another that we know that the alcohol hydroxyl group is not a good leaving group. So to make it good leaving group, what happened? We actually convert them into a good leaving group. So the most common way to convert hydroxyl group in a good leaving group are to convert them into the form of tosylate, mesylate, and triflate. What are tosylate? A tosyl group and a mesylate methyl sulfonyl group, and the triplet having a CF3 over here, and then we have the same case. Direct displacement, as I mentioned earlier, of the OH group without a nucleophile via an SN2 reaction is not possible, since hydroxyl group is a very poor leaving group. So, as I mentioned in the previous slide as well, that this nucleophile cannot depart or substitute this hydroxyl group. So this is the need that we have to convert them into the mesylate, tosylate, or triflate group to make alcohol as a good leaving group. So this is basically what happened, that alcohol when treated with the methyl chloride in pyridine to give you this mesylate or the mesylate ether as well, a mesylate group, which is being abbreviated as OMS as well. And similarly, this is known as the methane sulfonyl chloride. When alcohol treated with the paratoluene sulfonyl chloride in pyridine to ultimately afford this tosylate ether, which is also written as OTS. This the whole group can be written as OTS or tosylate as well. SN2 displacement of the mesylate or the tosylate in the nucleophile is possible, and a very even a poor nucleophile can depart this OTS or the OMS, whatever we have. Here are some specific example, and one we have the alcohol, which is basically chiral. The tosyl chloride, when reacted, of course, the same configuration we have. If it is R, then we have the R configuration of the substituted or the protected alcohol as well. And when this treated with the nucleophile, like in this case, we have the cyanide, this step is basically a crucial step in which the configuration will change. The R is being converted into the S configuration. So we can say the conversion of alcohol into the tosylate or mesylate will retain the configuration, while reaction of this tosylate or mesylate with the nucleophile will actually invert the configuration. Another example, when we have the alcohol on axial position, when treated with the methyl chloride, we have the inversion of configuration, axial remain as it is. When treated with the sodium thiomethyl, we have basically equatorial position, and this is basically changing its orientation. The next reaction is the conversion of alcohol into the ether. When alcohol treated with the strong base and later is treated with the alkyl halide, we can get the ether. This reaction also proceed via the SN2 reaction. Here R is limited to 1 degree and sometime rarely 2 degree of alcohol, but R prime from the alkyl halide could be 1 degree, 2 degree or 3 degree. One example, when this alcohol, which is the secondary alcohol, treated with the sodium hydride, the strong base hydride will capture this acidic proton and convert this sodium sodium salt of alcohol. And later this oxyanion of the sodium salt of alcohol will act as a nucleophile to depart this bromide ion to give you this corresponding ether, which is isopropyl, ethyl isopropyl ether. Another example, it is the intramolecular cyclization to give you the ether. The base capturing this proton from the alcohol to give you this oxyanion. Now this oxyanion is acting as a nucleophile to depart this chloride ion to give you intramolecular cyclization to give you the cyclic ether. Another example, then when this cyclohexane alcohol and iodine base capturing this proton, and this proton is acting as after removal of this proton, this oxyanion is acting as a nucleophile to depart this iodine to give you this cyclic ether. However, with the same side of hydroxyl group and the iodine or the halogen cannot form this epoxide, because this is the orientation of the molecule, that oxyanion will attack on the back side, while in this specific example, the both group are on the same side. So this is the limitation of this cyclic ether formation as well. This is the overall summary of the reaction when alcohol treated with the concentrated acid to give you this alkyl halide at room temperature, when alcohol reacted with phosphorus tribromide to give you this alkyl bromide, when alcohol treated with the thionyl chloride give you this alkyl chloride, in this specific example, the propyl chloride, when alcohol is reacting with the tosyl chloride give you the substituted alcohol, when alcohol reacting with a strong base and then later treated with the alkyl halide to give you the ether formation. That's all for the reactions of alcohol. Of course, we have so many other reactions of the alcohol which will be discussed in some other lecture. Thank you. Bye-bye.